Hello, and welcome to another Orca3D video tutorial. In this video, we'll walk through how to perform an Orca3D parametric speed and power analysis using Orca3D Grasshopper components. Before we can run a parametric speed and power analysis, we need a basic hydrostatics analysis. Our Intro to Grasshopper video walks through this process in detail. In short, we'll need geometry, either from a Grasshopper component like this planing hull assistant, or brought in from Rhino, which can be done in many ways. Then we'll need to define a load case or input condition. We'll use the sinkage, trim, and heel input condition generator. And finally, we'll need the hydrostatics calculation component. Just connect your geometry and input conditions, and double-check the mirror parameter. Enable it if you're using a half hull. My geometry includes port and starboard sides, so I'll set this to false. And with our basic hydrostatics analysis done, we're ready to start building up our parametric speed and power analysis. In the Orca3D tab of the Grasshopper ribbon, go to the resistance category. Here, you'll find components for different parametric resistance calculations, like Holtrop and Savitsky. We'll focus on Holtrop today, but other analyses follow a similar structure. Generally, the analysis will have an input generator, flowing into an input override, flowing into a calculation component. First, grab an input generator component. This component takes your geometry and the hydrostatics result from earlier and computes some preliminary values, like the immersed transom area at the load condition. These values are the mathematical inputs for the final parametric calculation. Now, some of these values, like Holtrop's stern shape coefficient, can be a bit ambiguous for certain geometries. So what if you want to manually redefine one of these values? That's where our next component comes in, the input override component. It sits downstream of the input generator component, and it allows you to manually override individual values in the input generator's result. If we specify -15 for the stern coefficient, the resulting Holtrop-Mennen input object reflects our new stern coefficient value compared to the original input object, while all other values remain unchanged. We'll carry on without the input override component for now, but remember that it can always slot in before the calc component. Next, let's add our Holtrop calculation component. Go to the resistance category and grab the calculator. At the top, plug in your parametric calculation input. This could also come from an input override component. And for Holtrop, also make sure to plug in your correlation allowance. You can use the Holtrop CA from the input generator, or use the ITTZ78 component. Then, enter a list of speeds for the run at the speeds parameter. You can manually enter this on the component by right-clicking the parameter and using one of these two options. You could also write a list in a panel and connect that, or use other Grasshopper components to make a list of values. Units for your run speeds are set in the Orca3D Properties window in the main app, as with all units in Grasshopper. The last two parameters are important parts of any parametric analysis. Your resistance design margin, which can be used to account for appendages, wind, waves, shallow water, or anything not accounted for by the parametric analysis, and your propulsive efficiency, which accounts for losses in the propeller and shafting and can be used to calculate the required installed power. More on these two in a moment. On the output side, you'll find Froude number, along with some values specific to each prediction method, like in Holtrop's case, CR. All of our parametric analyses include this block of 4 parameters. The first one, R bare, is the bare hull resistance straight from the parametric calculation. The resistance design margin is applied to this, which gives R total, and PE total, which represents the effective power required for R total at the design speed. Lastly, the propulsive efficiency is applied to PE total to give PP total, propulsive power total. These outputs are all lists of number values. You can connect these to a graph or to a panel component to view them. The panel opens up lots of opportunities. You can continually write the data to a file, which can be used by other programs or analysis tools. Just right-click the panel and select Stream Contents. Then choose where to save the data and what to call it. Thanks for watching, and check out the Orca3D channel for more how-to videos. Got more questions? Get more answers with the help resources in the description.